Wow, kinetics can get pretty intense, right? So we're going to spend a little bit of time here going through how to analyze that experimental data that we obtained last week. Now, the good news is we've been doing a lot of this in lecture anyway. We've been doing this method of initial rates using tables of data. So what's different now is you guys are going to be learning how those tables of data are created. You're actually going to create those tables of data yourself to analyze. So let's do a little bit of a review on what we actually did last week in our experimental lab. Remember, we were interested in determining the rate law, our reaction orders, all of that good stuff for this target reaction. But we weren't quite sure how to measure that, so we had to have kind of an indicator that we put in, but the reaction was going to be over so fast, so then we put in this loop reaction. And it's not really important that you fully understand everything that happened. But what's going to happen here with this loop reaction is we continue going into a circle until we use up this S2O3 that we have here. And when we add these two reactions together, the net reaction of what's happening is what we see here. Okay, so that's what we have. Let's think about some of the other things that we have. What was some of that data that you provided for me? Remember, you sat there with your flask and you watched and timed when you had color changes. So at time equals 0, you had 1 milliliter of this loop reagent in your flask. And as soon as that loop reagent ran out, then your flask turned color and you marked the time. And then you added another 1 milliliter of your loop reagent. So two things are kind of going on here that are going to become important for our analysis. The first is that our time was what we called a running clock. We had a running number of seconds. We didn't really monitor the difference between each of our time points. We just kept that clock running and noted how many cumulative seconds had passed. Similarly to that, we are going to consider the cumulative addition of S2O3. Even though we only added 1 milliliter at a time, we're going to consider the cumulative addition of that reagent. So what that really means is, again, we're going to be translating the amount of that loop reagent that we added directly to the amount of S2O8 that we used. So we can use a little reaction stoichiometry here to allow us to relate that, well, when we added 1 milliliter of this S2O3 reagent, it was really using up a certain amount, a certain number of moles of our S2O8 reagent. So that's what I've got kind of written down here. When our reaction first started and we had our first time point, our first color change, we used up 2 times 10 to the minus 4th moles of S2O8. There's a spot where you'll do calculations for this in your lab, so make sure you understand how those calculations work. But this is a cumulative running total of the amount of S2O8 that's used. So each time we add another milliliter of our loop reagent, we're using up another 2 times 10 to the minus 4th moles of our S2O8. All right, so what does this all mean and why did I need to bring my computer today? Well, we're going to be graphing this data, or I'm going to be providing you data that you will graph yourself. And what we're going to graph is the amount of S2O8 used. This is going to be a known variable. That's going to be the same for everyone and for every trial. And then what's going to be different is the amount of time that passes between changing color. Now, ideally, and I think you guys realize this as you were doing some of your experiments, there should be an even amount of time that kind of passes between each of those color changes, right? So we should be having a straight line here. Important kind of scientific concept. When you have a straight line, the equation for that straight line is y equals mx plus b. In this case, our y is the number of moles of S2O8 that are used, and then our x, that's our measured variable, that's what we were monitoring and measuring, was our time. So our slope here is going to be equal to the rate. Remember, the rate is just the change in the concentration of a species in your reaction as a function of a change in time. In this case, it's going to be the disappearance of this reactant. So when we plot all of those 8 data points that we had from our trials, we are going to be able to get a rate for that reaction. Okay, so what do we do with that then? All right, so this is how we create this table of data that you're going to be using for your method of initial rates analysis. All right, so 4 trials. You only performed one of those trials, and you're getting data from me that's going to be representative of what the entire class did. So everybody's going to be analyzing the same data set. So after we plot this data, and Dr. Brown has a great video that walks through how to actually plot this data and then get your slopes, which are going to be your rates. We're going to have these in here. Now we need to figure out how to fill in the rest of this table. What's the concentration of S2O8 that we have, and what's the concentration of I- that we have? Now, I'm going to highlight here in this video, because these are data that I had from a previous year, these are not the same data that you will have. So use this sort of as a way to learn how to do this, but the numbers that you're going to be putting in are going to be different since we use different concentrations and volumes of reagents for this year's lab. Okay, so we do know the stock concentrations that we had for each of these reactants that we're interested in. And we know the volumes that we used. So again, highlighting these are different volumes than you guys used in your lab. This is data from a previous year, but it still illustrates the point of how to do these calculations. So if you know the concentration of stock that you had, and you know the volume that you took of that stock, we can use our M1V1 calculation to figure out what the concentration of that diluted solution. Remember, when we're mixing all of these things together, they're diluting each other. So we have to consider what the total volume is, which is going to be 100 milliliters. And then for each of these, we can figure out what the new concentration is. All right, so make sure you understand how to do those calculations. You're going to do them for your unique data from this year's experiment, but you will be able to get concentrations then of each of these reagents as they are relevant for the 4 different trials. Remember, the slope of these lines have units of moles, okay? Because we are plotting moles of S2O8 as a function of time. So in order to get this into molarity per second, which is what we need to have for our rate, we actually need to divide by the volume that was contained in. So we're going to divide by 0.1 liters. So that's an important piece to make sure that you put in to your calculations. All right, so at the end of the day then, what do we really need to do? To determine reaction orders, you need to find a reaction where one reagent is being held constant in terms of its concentration, and another one, we are changing it. Okay, so again, this is going to be different for your experimental data for this year, but comparing what we had from last year, for example, if I wanted to figure out the reaction order with respect to S2O8, so I have to find an experiment where I am not changing the concentration of I-, okay, but I am changing the concentration of S2O8. This is actually the only one that I could have here for this, because look at the rest of these. These are all different concentrations of I-. I know that from the volumes that I added. So the only reaction where I am holding the concentration of I- constant is in reaction or in trial 1 and trial 2. So I have to use that to determine the reaction order with respect to S2O8. Now, for I2-, I should say that's just I- there. For I-, for that guy, whoops, that was way too big of an eraser. For I-, okay, I can compare 1 and 3, or I could compare 2 and 4. So let's take a look at that. Again, comparing 1 and 3, I can see that there I'm holding S2O8 constant. And then 2 and 4, I'm holding S2O8 constant, but I'm allowing the concentration of I- to change. Okay, so that's how the method of initial rates works. But essentially, this is the table of data you guys would have in lecture. You'd have a bunch of trials. It would say rate, it wouldn't say slopes, but you'd have rate data, and then you'd have concentration data. So that's all that we're doing here. All right, so let's put some fictitious data in here. You're going to have your own data, and you need to figure out how this is going to play out. Remember, here's our generic rate law, right? It's rate equals rate constant times the concentration of S2O8 raised to a power that is its order times the concentration of I- raised to a power that is its order. So we're going to do that comparison of different trials in order to determine those reaction orders. So how we teach this, or how I teach this in class, is I say we need to find, again, if we want to determine M, that means we want to be looking at the dependence of the reaction on the concentration of S2O8. The only option was to compare reactions 1 and 2, because that's where I'm changing the concentration of S2O8, but I'm holding the concentration of I minus constant. So what I like to think about is what's the fold factor difference in the concentration of S2O8, and then what is the fold factor difference in the rate. Okay, so the same thing is going to be true when we're looking for N, the order with respect to I minus. In that case, I can either use reactions 1 and 3 or 2 or 1 and 4. I think I might have a typo there again too. It's going to be 2 and 4. So 2 and 4 is going to be what I could compare there. Okay, so now what we have to do is actually get this information here. All right, let me fix this here so we don't see 2 and 4 again. I actually compared 1 and 3, so it didn't matter. But this is how we approach this in lecture, and this is how we're going to approach this here. So again, if I'm looking at determining M, I need to find the fold factor change in my concentration and compare it to the fold factor change in my rate. So I'm basically going to be taking the ratio of the concentration of the rates, the ratio of the concentration of those reactants, and then I find out what is the relationship between those. So what I can see here from this fictitious data is when I double the concentration, I double the rate. Okay, that is first order. Let's look at a similar one over here. When I double the concentration of my I minus, but again, keeping the concentration of S2O8 constant, I can see that I double the rate. So another situation where this is first order with respect to I minus. Okay, so you're going to analyze your own data to determine what the reaction orders are with respect to S2O8 and then I minus. All right, so if you remember what our next step was as we learned this in lecture, we basically are interested in determining what the rate constant is as well. So we have all of these pieces in our rate law, but many of these we can actually get from our experimental data. Remembering that we got M and N by doing this comparison of the dependence of the rate on the concentration changes, so that's the reaction orders. We actually have the concentration data that we actually used in our experiment, and then we have the rate data that we used in our experiment. So remember, we can calculate the rate constant by choosing any one of the trials and then putting in the relevant pieces of information and solving for K. So that's what we can do here, right? K then is the only unknown in the rate equation. We are going to solve for K using data from all of the trials and then average them together. So here's sort of an example calculation, right? If we're solving solving for K here, rate over the concentration of S2O8, these are both raised to the first power because it's first order, times the concentration of I minus, here is going to be our rate constant. Now, units of rate constants are important. Those units tell us the overall order of the reaction. So it's very important that we look and see what were the units of rate, molarity per second. What are the units of our concentrations? Because they are not squared or anything here, it's just going to be molar times molar. So the units of our rate constant end up being reciprocal molar, reciprocal seconds, which is the rate constant that we'll see for a process that's second order overall. All right, so putting this all together, all of these pieces, when we finally write our overall rate law, we want to include what this average K value is. So highlighting again, we've got all of these pieces in our generic rate law. When we write a specific rate law, we want to specify what those are. So we used rate and concentration data with the reaction orders that we got from our sort of method of initial rates to solve for our K. So we put all of these pieces of information together to write a specific rate law that now puts that value for the rate constant in there. So I know that's a lot, but hopefully this last little part was pretty straightforward because it's the same kind of calculations we've been doing in lecture for that concept of the method of initial rates.